Have you ever seen something that just shouldn't be possible? Well, today, we're diving into a scientific paradox that seems to break all the rules. And get this, it's hiding in something you see every single day, a simple glass of water.
You know, this isn't some new high-tech puzzle. We're talking about a phenomenon that was observed by the ancient Greeks, written about by the founders of the scientific method, and yet it's still one of the most stubborn, unsolved questions in all of physics.
So this is the big, baffling question. It goes against everything that feels like common sense. I mean, how could something with a longer path to freezing actually win the race? It just doesn't seem right. Let's unpack this. Okay, so this whole thing is officially known as the Mpemba Effect. And the reason it drives scientists so crazy is that it seems to fly right in the face of one of the most fundamental rules of heat transfer. It's a pretty basic concept, right? To get from, say, 80 degrees down to 0, you have to pass through 20 degrees along the way. And since cold water is already starting at 20 degrees, it should have a massive head start. And yet, sometimes it just doesn't. So how did this ancient puzzle get such a modern name? Well, the story doesn't come from some fancy high-tech lab. Nope, it comes from a high school kitchen, all thanks to the sharp eye of one student who just refused to believe that what he saw was impossible. What's absolutely wild is just how long this mystery has been hiding in plain sight. I mean, you've got thinkers from Aristotle to Francis Bacon who noticed it, but it was always just treated like a weird little quirk. It wasn't until a teenager in the 20th century came along that science was finally forced to take it seriously. So, picture this. It's a classroom project. Students are boiling milk and sugar to make ice cream. Now, most of them follow the instructions, letting their mixture cool down before putting it in the freezer. But Erasto Mpemba, he was in a hurry, so he put his boiling hot mixture straight into the freezer just to grab a spot. And that's when he noticed something that made no sense. His hot mix was frozen solid, while his classmates' cooler mixtures were still just liquid slush. So he did what any curious kid would do. He asked his teacher. And the response? He was pretty much laughed at. He was told to stop asking silly questions, that what he saw simply couldn't have happened. But Mpemba didn't forget. When a physicist named Denis Osborne visited his school, he asked the question again. And this time, the scientist was fascinated. They ran controlled experiments together, and what do you know? They proved it. The schoolboy was right all along. The effect was real, and it was named after him. Okay, so if the effect is real, what on earth is actually causing it? Well, this is where the detective work really begins. Scientists have come up with 4 main suspects, 4 competing theories trying to explain this whole paradox. The first theory is actually pretty straightforward. Hot water creates a lot of steam, right? Well, that steam is just water leaving the container. So by the time the hot water gets down to the freezing point, there's just less of it left to freeze. Think of it like 2 runners in a race. The hot water starts further back, sure, but it's constantly shedding weight by evaporating as it runs. So even though it starts with a disadvantage, it literally lightens its own load along the way. The second theory looks at what's happening inside the water. In a container of hot water, the warmer water rises and the cooler water at the surface sinks. This creates a current, kind of like a conveyor belt, that's constantly bringing the hottest water up to the surface to cool off faster. So the key here is that hot water is way more efficient at getting rid of its own heat. Cold water is more, calm. It just sits there, losing heat slowly. But hot water is actively churning and accelerating its own cooling process, especially right at the surface. Theory number 3 suggests we might not even be comparing the same thing. See, when you boil water, you're forcing out a bunch of dissolved gases, like carbon dioxide, and this change in the water's makeup could subtly change how it behaves when it cools and freezes. So the boiled water isn't just hotter, it's also purer, in a sense. And some scientists think that this lack of dissolved gases might raise the freezing point just a tiny bit or change how heat transfers, giving it that winning edge. All right, our final theory involves this really weird phenomenon called supercooling. Believe it or not, water can actually drop below its freezing point and stay liquid. To turn into ice, it needs a little trigger, a tiny speck of dust or some impurity to crystallize around. This theory says that cold water is full of these triggers, so it can get stuck in that liquid state. But boiling the water removes a lot of them, so when the hot water hits 0 degrees, bam, it freezes right away, no delay. So we have evaporation, convection, dissolved gases, and supercooling.
4 really plausible theories. So, which one is it? I mean, with all these ideas, the case has to be closed, right?
Well, this is where it gets really strange. The verdict is there is no verdict. After decades of research, physicists have basically concluded that not a single one of these theories can explain the Mpemba effect every single time it happens.
So let's just recap what we actually know for sure. The effect is definitely real, and it's reproducible. But it's fussy. It only works under very specific conditions, like the shape of the container or the type of freezer. Different theories might explain it in different situations, but the ultimate why, well, that's still a surprisingly heated debate.
Now, it's easy to just write this off as a weird party trick, a bit of scientific trivia. But the fact that this simple puzzle is so stubborn actually tells us something pretty profound about science and how we understand the world. Here is the real takeaway. Water. It covers over 70% of our planet. It makes up 60% of our bodies. We have studied it for thousands of years, and yet this simple little molecule still holds secrets that challenge our most basic understanding of physics. It's incredible.
And really, that leaves us with a final thought. The story of Erasto Mpemba is the perfect reminder that huge discoveries can come from anywhere. Mystery isn't just out there in distant galaxies. It can be right here in a glass of water, just waiting for someone curious enough to ask, why?